Um, Hello. Today we're going to go through one production issue from start to finish and see how we can apply dynamic tracing to get to the bottom of a problem. My name is Ivan, and I work at a company called Cloudflare, where I focus at performance and efficiency of our products. To give you some context, this is the key areas Cloudflare specializes in addition to being good old CDN service with free unlimited DDoS mitigation. We try to be at the front of innovation with technologies like TLS 1.3, quick and edge workers, making internet faster and more secure for both end users and website owners. We're also the fastest authoritative and recursive DNS provider. Our resolver 1.1.1.1 is privacy-oriented and supports things like DNS over TLS, not allowing intermediates to know which sites you go to. If you have a website of any site, you should totally use us. Here are some key numbers that can give you an idea of the scale we operate on. We have 160 data centers around the world and plan to grow to at least 200 next year. At peak, these data centers process more than 10 million HTTP requests per second. At the same time, the very same machines do 4.5 million requests million DNS requests per second across both internal and external DNS services. That's a lot of data, and to analyze it, we collect logs and ship them to core data centers for processing and analytics. I often get frustrated when people show numbers that are not scaled to seconds, so I figured I cannot win them, so I should just join them. Here you see numbers per day. My favorite one is network capacity, which is 1.73 exabytes per day. As you can see, these numbers make no sense. It gets even weirder where different numbers scale to different times, so you should just never do that. Now to set the scene for this talk specifically, it makes sense to tell a little about our hardware and software stack. All machines serving traffic and doing backend analytics are bare metal servers running Debian. At that point, we're running Jessie. We're big fans of ephemeral stuff, and not a single machine has OS installed in persistent storage. Instead, we boot from minimal immutable initramfs image from network and install all packages and configs on top of that into MFS with configuration management system. This means on reboot we can switch OS and it will start from a clean state. OS and the kernel as well. And the story starts with my personal desire to upgrade Debian from Jessie to the latest stable, which is Stretch at the time. Our plan for this upgrade was quite simple because of our setup. We can just build all necessary packages for both distributions, switch some groups of machines to Stretch, fix what's broken, and carry on to the next group of machines. We didn't need to wipe disks, reinstall anything, deal with dependency issues or conflicts. We even only needed to build just one OS image as opposed to image per workload. On the edge, every machine is the same, so that part was trivial. In core data centers, where our backend analytics runs, we have different machines doing different things, which means we have more diverse set of services and more diverse set of groups of machines that can do things. One of such groups was a set of Kafka clusters. If you're not familiar with Kafka, it's basically a distributed log system. Multiple producers append messages to the logs, and multiple consumers consume from these logs. For the most part, we're using it as a queue with a large on-disk buffer, so that gives us time to fix issues if consumers are broken. So, for example, we can have broken consumers for 6 hours and not lose a single request. We had 3 major clusters. DNS logs are small with just 9 nodes each, and HTTP is bigger with 106 nodes. You can see the specs for HTTP cluster at the time on the slides. 128 gigs of RAM, 2 Broadwell Xeon CPUs in NUMA setup, with 40 logical CPUs total. We opted for 12 SSDs in RAID 0 to prevent I/O thrashing from consumers failing out of page cache. We had a big problem before with spinning disks. That's the reason. In terms of network, we have 2 times 10 gig NIC bonded in setup for maximum throughput. It was not intended to provide any redundancy. We just need the whole 20 gig NIC. We used to have a lot of issues with being network bound, but in the end it was solved with aggressive compression with ZSTD. Funnily enough, we also opted out to have 2 times 25 gigs in the next generation, just because they tend to be cheaper than 2 times 10, even though we're not network bound anymore. You can check out the blog post about compression and Gen 9 machines we have. So we did our upgrade on small Kafka clusters and went pretty well. At least nobody said anything and user-facing metrics look good. If you were listening to talks yesterday, that's apparently what should be alerted on, like user-facing metrics. And CPU is not, so nobody noticed anything. On the big HTTP cluster, however, we started seeing issues with consumers lagging. So we looked at the metrics we had. This is what we saw. This is one upgraded node was using a lot more CPU than before. That's 5x more. By itself, this is not a big issue. You can see that we're not stressing out CPUs that much. Typical Kafka usage was around 3 logical CPUs, and that machine has 40. So that's a lot of headroom. Still, having 5x usage was definitely an unexpected outcome. For control data points, we compared problematic machine with another machine that had no upgrade, and intermediate node that received full software stack upgrade on reboot, but not OS upgrade, which we optimistically bundled with a minor kernel upgrade just for fun. Neither of these 2 nodes experienced CPU saturation issues, even though their setups were practically identical. So for debugging CPU saturation issues, we depend on Linux perf command to find the cause. It's included with the kernel and on end user distributions. You can install with package like Linux base. The first question that comes to mind when we see CPU saturation is what is using CPU. In tools like top, you can see which processes occupy CPU, but with perf, you can see which functions inside of these processes sit on CPU the most. This covers kernel and user space, and well-behaved programs that have debug symbols will be shown here. And if you don't have debug symbols, you're just going to see addresses like on the bottom. Here you see top-like output from perf with the most expensive functions in terms of CPU time. Sorting is a bit confusing because it sorts by inclusive time, but we're mostly interested in self-time, which is time taken by the function at the tip of the stack. In this case, the most time is taken by a spin lock slow path. Spin locks in kernel exist to protect critical sections from concurrent access, and there are 2 reasons to use them. One is critical section is small enough and it's not contended, and another is that lock owner cannot sleep, like interrupts cannot sleep. If spin lock cannot be acquired, caller just burns CPU until it can get the spin lock. It sounds like a questionable idea at first, but there are multiple legitimate uses for this mechanism. In our situation, it seemed like spin lock was really contended, and half of CPU cycles were just not doing any useful work. We don't know what lock was causing this to happen, but there are also other symptoms, so let's look at them. So if anything happens in productions, it's always a good idea to look at dmask. Messages can be a bit cryptic, but they at least point in the right direction. That's 90% of the problem solved. In that particular case, we saw RCU stalls, where RCU stands for read copy update. I'm not exactly an expert in this, but it sounds like another synchronization mechanism, and it can be affected by spin locks we mentioned before. We've seen rare CPU stalls earlier. And our suboptimal solution was just to reboot the machine, and 99% of the time, the issue just goes away. So it doesn't warrant a thorough investigation. However, in this case, we had different symptoms as well, so we looked at that. While looking deeper into Gmest, we noticed issues around writing messages to the console. This suggested that we'll log in too many errors, and the actual failure was earlier in the process. Armed with this knowledge, we looked at the very beginning of the message chain, and that's what we saw. If you have newer machines, you can immediately see a shrink node function and have a minor PTSD episode. What you should be looking at is the number of missed kernel messages. There were so many errors, journal D wasn't able to keep up. We have console access to work around that, and that's where we saw page allocation stalls in the second log accept. You don't want page allocations to stall for 5 minutes, especially if it's order 0 allocation, which means it's just one 4 kilobyte page. Comparing to our control nodes, the only two possible explanations were a kernel upgrade, which was minor, and the switch from Debian Jessie to Debian Stretch. We suspected the former since CPU implies kernel usage. Just to be safe, we rolled both the kernel back from 4.9 to known good 4.4 and downgraded all affected nodes back to Debian Jessie. This was a compromise to minimize downtime and effect on production nodes. And then we proceeded to look at the issue in isolation. To our surprise, after some bisecting, we found that iOS upgrade alone was responsible for our issues, and the kernel was off the hook. Now that all remained that is to find what was going on. So flamegraphs are a great way to visualize stacks that cause CPU usage in the system. We have a wrapper around Brendan Gregg's flamegraph scripts that remove idle time and enable JVM stacks out of the box. This gives us a way to get an overview of CPU usage in one command. And that's how full system flamegraph looks like. We have Jessie in the background on the left and Stretch in the foreground on the right. This may be hard to see, but the idea is that each bar is a stack frame, and the width corresponds to the frequency of the stack's appearance, which is a proxy for CPU usage. You can see a fat column of frames on the left in Stretch that is not present on Jessie. We can see it's the send file syscall, and it's highlighted in purple. It's also present and highlighted on Jessie, but you can see it's so small there. Flamegraphs allow you to click on the frame, which will zoom into stacks containing that frame, generating some sort of sub-flame graph. So let's click on send file and Stretch and see what's going on. And that's what we saw. For somebody who's not a kernel developer, this looks like just a bunch of TCP stuff, which is exactly like it looks to me. Some colleagues suggested that the difference in the graph, in the flame graphs, could be due to TCP offload being disabled, but we looked at that, and it was the same absolutely between Jessie and Stretch. We can also see some spin locks at the tip of the flame graphs, which reinforces our initial findings with perf-top. So let's see what else we can figure out from here. To find what's going on with the system, we'll be using BCC tools. Linux kernel has a VM that allows you to attach lightweight and safe probes to trace the kernel. eBPF itself is a hot topic, and there are talks that explore it in great detail, and these slides will link to them as well. So to clarify, VM here is more like a JVM and less like a KVM that provides hardware virtualization. So you can compile code down to this VM from any language that supports it. So don't look surprised when one day you'll have JavaScript running in the kernel. For the sake of brevity, let's just say that there's a collection of readily available utilities that can help you debug various parts of the kernel and underlying hardware. And that collection is called BCC tools, and we're going to use some of this to get to the bottom of the issue. On this slide, you can see how different subsystems can be traced with different tools, and that pretty much everything is covered. To trace latency distributions of send file, syscalls between Jesse and stretch, we're going to use func latency or func latency. It takes function name and prints exponential latency buckets for function calls. So here we print latency histogram for do send file, which is a send file syscall function in microseconds. You can see that most of the time, most of the calls on Jesse hover between 8 and 31 microseconds. Is that good or bad? I don't know, but it's a good way to find out is to compare it to another system. Now look at what's going on with stretch. I had to cut some parts because histogram was not fitting in the slide. On Jesse you saw most of the calls complete under 31 microsecond. Here you can see that number is 511 microsecond, which is 16x jump in latency. In the flame graphs, you can see timers being set at the tip, and what timer function is responsible for that. With this, timers taking logs. We can count number of function calls instead of measuring the latency, and this is where func count comes in. Feeding more timers argument, we can see how many function calls were every second. Here you see Jesse on the left and stretch on the right. On stretch, we installed 3 times more timers than on Jesse. That's not 16x difference, but it's at least something. If we look at the number of logs that were taken for these timers by running func count on log timers base function, we can see an even bigger difference, around 10x this time. To sum up, on stretch we installed three times more timers, and the logs were 10 times more contended. So it seems like we're definitely onto something here. We can look at the kernel source code to figure out which timer is being scheduled based on the flame graph, but that sounds like a tedious task. So instead we can use perf tool again to gather some stats on it. There's a bunch of trace points in the kernel that provide insight into timer subsystem, and we're going to use time start because it just kind of makes sense. Here we record all timers started in 10 seconds and then print function names, the function names that were triggered for with respective counts. So on stretch we installed 12 times more TCP write timer functions. That sounds like something that can definitely cause issues. Remember, we're on bandwidth bound workload where interface is 20 gigs, and we saturated to almost to the full. And that's a lot of bytes to move. So if we look specific flame graphs of timers, we can see the difference in their operation. It's probably hard to see, but TCP push 1 really stands out on stretch, so let's dig into that. The tracers showed huge variations of TCP send message and TCP push 1 within send file, which is expected from the flame graphs before. If you can see, we're using the same func count tool. To further introspect, we leverage the kernel feature available since 4.9, an ability to count and aggregate stacks in the kernel. PCC Tools has a stack count tool that does exactly that, so let's use it. So the most popular Jesse stack on the left and the most popular stretch stack on the right. There were a few much less popular stacks, but there's only so much I can fit in the slides. Stretch stack was too long, and triple dots is the same as highlighted section in Jesse stack. They're mostly the same, and it's not exactly fun to look for the difference, so let's just look at the difference on the next slide. We see 5 extra functions in the middle of the stack, starting with TCP send page, and it's time to look at the source code. Usually I just Googled the function name, and it gives me a result to alexanderbootland.com, where I just swap latest to my kernel version. Source code allows you to click on identifiers and jump around just like IDE. This is how TCP send page function looks like. I pasted it verbatim from the kernel source. From TCP send page, our stack jumps into sub no send page. If you look up what netfsg means in this condition, you'll find it's segmentation of load. And segmentation of load is a technique where kernel doesn't split TCP stream into buckets, but instead it offloads the whole buffer to NIC to do this job. This makes a big difference when you want to send a large chunk of data on high-speed links. And that's exactly what we're doing, and we definitely want to have it enabled. So let's take a pause and see how we configure a network on our machines. Our 2 × 10 gig NIC provides ETH2 and ETH3, which would then bond into bond 0. On top of that bond 0, we create 2 VLAN interfaces, one for public internet and one for internal network. And it turned out that segmentation offload was enabled only on a few NICs we had, ETH2 and 3 and bond 0. When we checked NIC settings, for offload, we only checked physical interfaces and the bonded one because that made sense. But we ignored VLAN interfaces where offload was indeed missing. So we compared ETH tool output for VLAN interface, and there was our issue in plain sight. So we just enable offload by enable scatter gather, which is SG stands for, and be done with it. Like, easy, right? Imagine our disappointment when this didn't work. So much work with clear indication what the issue was, and it just didn't work. So the last missing piece was just offload changes are applied only on connection initiation. So we turn Kafka off and back on again to start offloading and immediately saw positive results, which is green line here. This is not 5x change. I mentioned at the beginning because we were experimenting on a lightly loaded node to avoid disruptions to production. Our network interface is managed by systemd network D, and it turns out the missing offload settings were just a bug in systemd in the end. It's not clear whether it's upstream or Debian issue that's responsible for this. In the meantime, we work around the issue by enabling offload manually on boot. Well, not manually, automatically on boot if it's disabled on any interface. Having the fix enabled, we rebooted our logs Kafka cluster to upgrade to the latest kernel, and on 5 days CPU usage history, you can see positive results. On DNS cluster, the results were even more dramatic because it had higher load. And on the screenshot, only one node is fixed, but you can see how much better it is compared to the rest. The first lesson here is to pay closer attention to metrics during major upgrades. We did not see any significant CPU changes in moderately loaded clusters and did not expect to see any effects on a fully loaded machines. In the end, we were not upgrading Kafka, which is main user CPU user, or the kernel, which was consuming system CPU. The second lesson is how useful perf and BCC tools were at pointing us where exactly the issue is. These tools work out of the box. They are safe and do not require any third-party kernel modules. More importantly, they do not require operator to be a kernel expert. You just need some basic understanding and just like Google the function name. Another lesson is how important TCP offload is and how its importance grows non-linearly with the traffic levels. It was unexpected that supposedly purely virtual VLAN interface could be affected by offload, but it turned out they were. Lastly, we used our ability to swap OS and the kernels on reboot to the fullest. Having no need to install OS meant we didn't have to reinstall it, could iterate quickly. So internal blog post about this incident was published in August 2017. Heavily truncated external blog post went out in May 2018. And that external blog post is what this talk is based on. And all of it to illustrate how the tool we brought can be used. If during debugging we used BCC tools to count timers, firing the kernel ad hoc, we could have had a metric for that and also noticed the issue sooner by just looking at the graph. That's where eBPF exporter allows you to have. You can trace any function in the kernel and user space at very low overhead and create metrics in Prometheus and Open Metrics format from it. For example, you can have histogram latency histogram for disk I/O latency as a metric, and that's not normally possible with procfs or anything else. Here's a slide from my presentation on that, which shows the level of detail you can get. On the left, you can see I/O wait time from proc disk stats, which is what Linux provides out of the box. And on the right, you can see a heat map of I/O latency, which is what eBPF Explorer allows you to have. With the histogram, you can see how many I/Os landed in particular bucket, and things like multimodal distribution can be seen. There's a little bit of that here. You can also see how many I/Os were above some threshold, so you can have alerts on that if you want to. And the same goes for timers. Kernel does not keep counts of that firing anywhere in the kernel itself. That's all I had for today. On these slides, you have some links on the topic. Slides with the speaker note, everything I said will be available on the LISA website. I'm sorry you have to hear from me and not just read it. I encourage you to look at my talk on eBPF Explorer itself, which goes into detail about why histograms are so great. It involves dinosaurs' GIFs in a very scientific way, and you probably do not expect that, so make sure to check that out. My colleague Alex will be doing a training on eBPF Explorer tomorrow. If you learn more about that, please come and talk to us. If you want to learn more about eBPF itself, there are some links, and you can just talk to me or Brandon Greg. And that's it. Thank you.